Delta G. In solution, you're going to be thinking about K sub C. If it's all gas phase, you can link it to K sub P if you would prefer. And if you're wondering about the situation, if there's a little of both aqueous and gaseous, well, guess what? That's why you take PChem. It's a little too complicated for this. And in this case, we're trying to just say, okay, everything is either in a gas phase or everything is aqueous. No mixing. We have a standard free energy of formation of ammonia, and we have a number for it. And it says, what's the value of K sub P for the reaction at 298 Kelvin? There's the reaction. That's our old friend making ammonia. And I found out from this what it is for making a mole of ammonia. So I will be calculating K sub P because these are gases. I'm trying to make just 1 mole of this. So I need to change the stoichiometry to match. So it's a half a mole of the nitrogen, 3/2 of a mole of hydrogen, and then 1 mole of NH3. I have a formula, delta G of formation, kilojoules per mole. I am told that what I want to do is take delta G of formation and divide by RT. This is a negative, that's a negative. I'm going to have to change it to a positive, so that's important to be careful with. And I don't like kilo very much, so I'll turn it into regular joules. That's going to be divided by R and T, 298 Kelvin. Which R am I going to use? This is in joules, so I had better use the R value that has joules in it, so they will cancel out joules per mole Kelvin. Notice every single unit cancels out. We need to make sure all the units cancel, otherwise this is not going to be right. And then when I actually calculate this, I get a evil number. Oh, evil number. And then I go back and I use the formula. K sub P is just going to be E raised to this negative G over RT, which I now know is 6.66. Round it back and you get 780. Well, we just got through figuring out K from delta G, so of course, why not do it the other way around, right? What's delta G if I know K? We write down our formula and I'll just put reaction here. And it's going to be minus RT and the natural log of K. The R that I use, have to make sure that the units are going to cancel, so it's going to be the 8.314 joules per mole Kelvin again. The T is the 298 they just told me about, and that's going to cancel out the Kelvin. And then the natural log of this K that they gave me, 0.1484. So you see this will give it to me in joules per mole, which is typically the thing we expect for a delta G. I'm just going to keep these and the 298. And then this natural log ends up being a negative number, negative 1.908. And that will be 4,730. Now that would be joules per mole. These delta Ks are usually in kilojoules per mole, 4.73 kilojoules per mole. There's a new way to calculate what delta G for a reaction is. What was the old way? If I used the Gibbs free energy information from the appendix of the book. If I did that, I would be going back to saying that delta G for a reaction is dependent on what's going on with the products and subtracting what's going on with the reactants. Okay, this is 2 moles that was the products. And I would go look up the delta G of NO2. On the reactant side, it would just be 1 mole. The delta G when I go look up N2O4. I get 2 moles times 51.3 kilojoules per mole and minus the 97.8 kilojoules per mole. So here's the 102.6 minus the 97.8, and I get 4.8 kilojoules per mole. So you can see it's very close to the same number that I got using K.